So let's think of the particle that is forced to live between x equals 0 and x equals L. And let's imagine that we have two eigenfunction superpositions. So we have states, let's consider states of this sort. So we have A psi n of x e to the minus I e n t over h bar plus B psi m of x e to the minus I e m t over h bar, where psi n and psi m are eigenfunctions of energy. With energies En and Em, we know how to get those values. And we want to ask, how does the probability, let's say, of finding the particle between 0 and L over 2, how does that, right, so we're integrating the probability density, how does that, let's ask, how does this depend on the mass of the particle? So, of course, the probability density is just psi star xt psi of xt. When we apply that to this function, of course, we're going to get a cross term that involves the cosine of the energy differences. So it looks like the mass of the particle will be in this calculation because it appears in En and Em. But let's remember that if, say, N and M are even or odd, so they have the same parity, then this means that we are building, right, this function here is built out of functions with one parity. It's either even or odd parity. But if we have one parity, then that means that the functions can't prefer one side or other of the well. So it must be true that this quantity gives us 1/2 if we can't distinguish one side or the other, given the parity. And that means that it's not a function of the mass. Whereas if n, say, is even and m is odd, or vice versa, then there's time dependence here, right? What follows is that this integral will be time dependent. We know how to find that, right? There are two terms that don't involve time, and then there's the third term, which is the interference term that has the time dependent part, and that part is, well, I don't want to say proportional to, but say independently, there's a third term that looks like cosine of the energy difference times T over h bar. And so clearly we know from the energy levels that the energy is proportional to 1 over the mass. And so this quantity is the angular frequency. And so the angular frequency goes like 1 over the mass. And so the time-dependent part involves a frequency that is inversely related to the mass. So the greater the mass, the smaller the frequency. So there's the oscillation frequency there that does depend on the mass, but it depends on whether you construct these superpositions with a fixed parity or not.